Autonomous flying. Let's start by defining what's autonomous flying. Well, it's the ability of a drone to make maneuvers without human at the control. So for example, let's say if you want to fly a drone just above you or nearby while you're biking or hiking. Now, you want your drone to follow you and at the same time to avoid obstacles while flying. Now, to achieve that, you need to make sure that your drones are smart enough not only to detect object first, but to make the action at the right time of the object in its path. Now, what are the challenges of autonomous flying? First of all, flight control. How you can make actions to control the drones. What system and platform I can use? Well, the good thing that for us is that there is open source system that right now available that we can use to control UAV flight or drone flight, like for example ArduPilot. It's a completely C++ open source platform to control drones. You just need to set the starting point and the destination and monitor your flight and do the remote control. It's very powerful and stable, and with it we can run any algorithm or use our own program to control the drone actions and change for example, the altitude and the speed. The second challenge is the smart flying. What I mean by smart flying is the ability to fly independently, just by knowing the goal without making any accident. So it's independent flying, not controlled by a human, and no accident, and it just goes to the goals directly. Well, typically it should avoid objects and also find the shortest path to the goal. And of course, it should recognize its environment. Now let me show you how this works. This is an example of smart flying, and as you see, there are three different paths: red, green, and yellow. All of them are avoiding objects, but I would say that the best one would be the green one, or maybe the red one, because you want it to be smart enough to avoid objects and go to take the shortest path. Now, these are some other challenges of autonomous flying: the environment, the location of the environment, speed, decision making, and object detection. The environment, you need to know what environment you are dealing with: trees, mountains, desert, flat or curved ground. The location in the environment is very important as well, because where are you, above ground, underground, and all other attributes that you are dealing with. Your speed also is a challenge, because the higher the speed is, the difficult is to control your drone. Same thing for decision making. You need to make decision very fast, and the faster you are making decision, the good that you are in controlling your drones, and the good at you avoiding objects and object detection. Because think about it, in order to avoid object, you need to detect it first and know its location exactly, the X and Y and Z. So you need to know its location in three-dimensional world, and based on that you can make the right action. Without this, you will not be able to avoid the object if you're not detecting it correctly. So all these are the challenges of autonomous flying. How are we gonna overstep these challenges, and how are we gonna design our algorithm accordingly? So this is the object avoidance, and this is an example of what we are trying to achieve. As you see, there is object in its way and it's trying to avoid it. So typically we want to avoid the object and go to the same path to the goal. So we need to do this maneuver seamlessly and at the same time while maintaining our path to the goal. Okay, reinforcement learning. Now, we need to know how to make the autonomous flying algorithm smart enough to understand what's actually supposed to do as per the environment. So reinforcement learning is AI. In AI, it's basically the type of machine learning in which your software learn how to perform to do a task through a repeated trial and error interaction without any human intervention and dealing with a dynamic environment. So typically you want to make a series of decisions that maximize a reward for the task without any control and without also being programmed to achieve the task, which is very important as well. So let's see this picture and see a real word equivalent situation here. Well, the goal of the reinforcement learning is in this case to train the dog, which is the agent, to complete a task within the environment, which includes the surroundings of the dog as well as the trainer. First, the trainer will make a command which the dog will observe, and now the dog then respond by taking action. If the action is close to the desired behavior, the trainer will likely provide a reward, which could be a treat, for example. If not, then no reward. At the beginning of the training, the dog will likely make a random actions, likely rolling over when the command say set, which is not supposed to do because she doesn't know what to do and she's trying to learn. As it's trying to basically, the dog is trying to associate a specific observation with the action and reward. So this mapping between observation and action with reinforcement learning, it's called policy. So from the dog perspective, the ideal case would be one in which it would respond correctly to every command that gets as many treats as possible. Learning training it could be tuned by the dog or by the dog policy so that it learn the desired behavior that will maximize some rewards. After the training is complete, the dog should be able to observe the owner and make the right action or the appropriate action when the command is set as says. So basically the dog knows what's going on. So this is also another example of reinforcement, how reinforcement works for self-driving. The algorithm will try to observe the environment and then learn from the environment. And it continues the recycle of try and errors and until the car knows what to do. So imagine this is our environment. This is what the drone, this is when the drone is flying, and this is exactly what it sees, right? From the camera. And if you look closely, you will see that this is a 3D, but each frame is 2D. So we have green and then purple and then blue and then brown and orange, and every frame or every layer, every frame and every layer of that 3D world is a 2D. And if we can take a picture of this 2D world and convert it to 10 by 10 and then take 1 square from that 10 by 10 and convert it to 4 by 4, then you will have a small grid of the big grid in which you can use our reinforcement learning policy. And this is how the environment looks like. The policy for the for the two-dimensional grid, and number of how many two-dimensional grid will depend on the speed of the agent or of the drone, which is in this case the Z value, because the Z value is determined by the drone speed and the distance to the object. So as we said, every layer of the two-dimensional layer is gonna be determined by the policy that we're gonna make, and then we're gonna make the action for every 2D layers while flying in 3-dimensional world. So this is how it's look like. Now, how to make the right decision in the grid? So if you have a policy for every layer on the three-dimensional world, then you can ultimately navigate the drone. So we need a policy like that to show us the goal, the end state, and where to go every time we need to make action. So this is what you want to do. And now next, I'm gonna explain how to make this policy. So if you are looking at this, you will see that the whole environment is basically now we're working with a 2D grid, and it's a 4x4 grid. Each square in the 4x4 grid is state, and if there is any obstacles, then it's the -5 reward, and if there is no obstacles, then it's a positive reward. And we will make action based on the policy. The z point is calculated based on the speed and how fast we go. So how to make a policy? You need to define state, reward, and penalties. So the state would be, in our case, in the 4x4 grid, we will have the 16 different states, and each one have a positive or a negative reward. And it depends on if there is obstacles in that location or not. So if there is obstacles, there is a negative, otherwise it's a positive. And it's exactly as the dog example, we will start by doing a random, then we will optimize to get the maximum reward. So basically we're gonna run it for 1,000 times until we get the optimum policy. So as you see here, this is the workflow of the algorithm and how we're gonna identify where is the obstacles. And if we have obstacles in our way, then we check the policy, what to do in that particular case or in that particular location, and as per the policy. So if I'm, for example, in the state and I have obstacles in that specific location, then what's the policy for that? Then we will get the policy and make the right action. If there is no obstacles, then the agent or the drone will try to maintain same speed and same altitude as it is until it reaches the destination or the goal. So now I will show you the code and how this works in action. So let me take you, I'm looking for it now. Okay, so this is the one. Okay, let's run the code now, and this is and this is basically for two-dimensional grid. As I explained, the three-dimensional world just small number of players, and you have to consider the speed and the distance to the obstacles. Okay, so now as you see, the drone is moving in the two-dimensional world, and it's avoiding object. Basically, when it's as you see now, it's doing the needed maneuvers. It's referring to the policy, and now it's continue to its path, and it will do the same thing for the second object. It will try, once object detected, it will refer to the policy and make the action accordingly. And same thing with the third obstacles. Okay, now I see object, I'm gonna refer to the policy tells me to go down and then right, and the same thing with the last object. So it does make the right action at the right time without any control in this two-dimensional world. So now let's take the three-dimensional world concept and try to how we can apply this policy. It's very simple. You need to find the best decision. So imagine that you are flying in three-dimensional world and you see an object in front of you. Now you have multiple actions in this particular state. and 2, 3 of all of them, they give me the same positive reward. I'm having now 5 different end state, and all of them, they give me the same reward. But how to determine the right action? Well, this is going to be based on distance. So distance to objects will determine best end state. Then we get the policy according to that. So best action would be, of course, the shortest time that will get me to the end state, which is mathematically speaking, distance by speed. So the logic behind it is very simple. First, you need to find the location or the agent location in the 2-dimensional grid, in which square of 4x4. Then you find the obstacles or the barrier location in the grid, in the same 4x4 grid. Based on that, you get the policy. So do you remember this example? This slide showed the same thing. So this is 4x4 grid, and then the true green sign is the end state, and the red X is the obstacles. So based on the location of the obstacles, and if there is obstacles, then X. There is no obstacles, then is a true sign. Then that would be the policy. So I have a policy for every place that the obstacles could be, and then once the agent refer to the policy, it can make the right action based on the location of the agent in that specific 4x4 grid. So this algorithm is totally based on camera only. There is no other sensors like sonars or any other sensors. Just only we are using camera to detect objects. And also we are using policy iteration algorithm for reinforcement learning. You can refer to that, like there's so many documents about what are the how to make a policy iteration algorithm and how you can use it in your environment. Now the next step would be we need to integrate this algorithm with object detection algorithm. There are so many available algorithms that we can use. For example, TensorFlow object detection. It's a free algorithm it's open source algorithm that you can use to identify what is the object and what is exactly the coordinates of the object, X and Y and Z. There are some other commercial algorithm that we can use. For example, this one from Microsoft Azure, which is basically a platform as a service. So you upload your software in Azure, or you don't need to upload your software. You just need to use the API for Azure Computer Vision, and then you can utilize their object detection, and it will give you the same output that you need to identify what is the object in the grid. And also the next step would be running this algorithm in 3D world, something like Microsoft simulation, and try to see how effective it is in this 3-dimensional world. This is exactly something you need to do before the real flying, and that would be the next step, which is flying the drone in actual real life environment, and then see how good it is. So so with that being said, I think we covered the details of this algorithm. I will be in the comments of this YouTube, I will be adding the GitHub link to the source code, so you can see how this works in action. Thank you very much for watching, and if you have any question, you can ask me in the comments. I'll be happy to respond to your question. I hope you have amazing summer so far. Thank you very much for watching, and whether it's a night or a day, have a good one. Goodbye.